Alright, this will be a very short video about addition of bromine and water across an alkene, just like you saw for the addition of bromine across an alkene, except this gives us something called a halohydrin. And I'm not entirely sure where the word came from, but halohydrin refers to a molecule that contains a bromine and an OH from addition of bromine and water. And the halogen could also be chlorine here. The mechanism is exactly the same as you saw for addition of a normal bromine across the double bond, forming the intermediate bromonium ion. So I'm just going to draw that out over here. And I just want to spend a minute on the part of the mechanism that gets most people mixed up, or at least the step that gets most people mixed up. What we have here is the cyclic bromonium ion that you always see anytime you add bromine across a double bond. And usually what happens at this point, if it's just bromine, is the Br minus comes in and attacks here to form the products. Now, when you have a whole host of water around, as this is done partially in water, you have lots of water and you have Br minus around as well. And the water is probably present in a much larger amount than the bromide is, and so the water will selectively come in. Now, because these two, this and this, are actually different, the product that we actually form, it's actually going to, this water is actually going to attack one of these two carbons predominantly. Now, this is the bit that I want to try and make sure you all understand, because the question may arise as to whether this is a Markovnikov product or not. Markovnikov or not. Now, usually you've seen Markovnikov with respect to addition of hydrogen and something else, but in this case the Markovnikov rule can actually apply with respect to the species that attacks once you have your positively charged species. So normally you have a carbocation here, which the nucleophile then comes in and attacks the carbon bearing the plus charge. That tells you have a Markovnikov product. Now obviously the water is not going to attack the plus charge on the bromine, and it's going to attack one of these two carbons to break a bond and relieve the plus charge on the bromine. The question is which one? And for most people, the first answer is, well, it's going to attack here simply because there's less steric hindrance here. Now, whilst that is true, you can see from what the answer says that that's clearly not the case. The water is actually attacking this carbon, all right? And so we need some sort of rationale as to why that's the case, all right? And the way to explain it is, when this bond breaks, we would form a tertiary carbocation here. If this bond were to break, we'd form a secondary carbocation here. So therefore, the carbon that would potentially form the most stable carbocation will also have the most stable transition state, with the one that can absorb the plus charge the best. And so it seems somewhat counterintuitive, but it follows stability logic in terms of carbocation stability. So this goes down and attacks here, again because you would form a more stable carbocation at this carbon, and thus therefore this would be attracted to it, and it will break that bond. Now, because once again the bromonium ion is pointing up, that means our water is going to add from the bottom. So we should show it on a dash, all right? And that's what we're going to do. So we're going to show the bromine that now is no longer attached by two bonds, but is only attached by one, the way it should be. And then we'll have my attempt at a dash here, our water, which is now like this, okay? And because of that, what do we have on this? We have a plus charge there. Well, all we need now is something to come along and remove that hydrogen, because that's going to get us to here. Now, there's actually a couple of options as to what you want to do here. You just need some species. There could be some more water around that goes and grabs that hydrogen. You could use the Br-. It doesn't really matter which one. One of those two species will come along, grab that hydrogen, break that bond, and give you the product here. So once again, when you ask the question, is this a Markovnikov product or not, you want to ask yourself, which carbon is the nucleophile attacking in the second step? Is it attacking the most stable carbocation, or is it attacking, or is the nucleophile adding in the most substituted carbon? If that's yes, it's a Markovnikov product. Or is it adding in the least substituted position, in which case it's anti-Markovnikov? So you can see this is a Markovnikov product. Yes, it is. And that is halohydrin formation across a double bond.